Hello everyone, good afternoon. Thank you for joining us today. Hope I'm audible and the screen is visible to everyone. I'm Kavita and I handle marketing at Trident Infosol. I'll be your host for this session on advanced techniques for EMI, EMC mitigation in modern electronic systems. Before we get into the main topic, let me quickly tell you a bit about who we are and what we do. Trident Infosol is an established engineering solution provider with over 2 decades of experience. Having started our operation back in the year 2000, we focus on 3 major verticals: software, hardware, and manufacturing. We also specialize in product design and manufacturing and product support and services. Basically, we help our customers through the whole journey from picking the right solution all the way to after sales and support. Our head office is in Bangalore with a registered office in New Delhi. We also have a sales and support office spread across Pan India. We are a 230 plus strong team and more than 60% of us are engineers, which really help us when we are working on complex technical solutions. While we mainly work in sectors like industrial, automotive, embedded systems, and especially defense and aerospace, our strength lies in building solutions that are tough and reliable. Over the years, we have had a chance to work with some incredible clients, both in government and private sectors. We support government organizations like DRDO, ADA, BEL, HAL, and many others, especially in aerospace and defense projects. On the private side, we work closely with some of the biggest global players, and you can see some of them listed on the slide. This mix of clients shows how flexible and reliable our solutions are, and how we committed are building long-term partnerships. Now, a quick look at our software side. We offer tools that covers entire product development cycle from requirement capturing, traceability, and system engineering, design, debugging, and hill testing. Today, we are zooming in CST Studio Suite. It's a powerful simulation software used widely for electromagnetic and multi-physics problems. It's got everything you need packed into one interface, and it's used by leading companies worldwide. This session is all about diving deeper into CST, how CST can help with EMI, EMC challenges. Also, we are proud to be an exclusive partner of Trident Dassault Systems in India. Before we get started, let me quickly introduce today's speaker. Anubhav Jain comes with vast experience in RF engineering and EMI, EMC compliances. He graduated in Electronic and Communications from Birla Institute of Technology. His research includes some pretty advanced topics like metamaterials and Zora antennas, and he has worked on developing 3D electromagnetic simulation tools at SERC. At Trident Infosol, he now supports customers with technical training and support for CST and DIMOLA. We have got a lot more exciting sessions lined up after today. We'll be covering topics like requirement analysis, traceability and validation, model-based system engineering, multi-domain modeling simulations, debugging on multi-core systems, advanced timing analysis, and of course, hill testing. So if you have any that sounds useful for you, follow us on LinkedIn. We post all our updates there, and you can also catch up on the past sessions on our YouTube channels. If there is something specific you are working on or need any help with, don't hesitate to reach out. We are always happy to support you. Before we jump in, just a quick note, if you have any questions come to your mind while you are listening today, feel free to drop them in a chat session anytime. We'll circle back and go through all of them at the end of this session. All right, let's get started. Over to you, Anubhav.
Okay, so thanks for a wonderful introduction. I thank everyone who has joined this webinar. A hearty welcome to all of you. As Ms. Kavita introduced me, I work as an application and design support engineer at Trident Infosol and handle support and services, support, sales and services for CST. CST, a 3D electromagnetic software tool by Dassault Systems. So if you're wondering what CST is, CST stands for Computer Simulation Technology. Webinar. So let's understand what we'll be covering in this webinar. Firstly, I will give you a brief introduction to EMI about industries. So few industries that we have taken up for today is A&D, Aerospace and Defense, TNM, Transportation and Mobility, HT, High Tech, and Healthcare and Life Sciences. So in these, we will be seeing the trends of the industry and the challenges that they're facing. And we'll try to understand how we can combat such challenges without affecting the pace of development and production to market. So then we have some case studies on EMI/EMC. So that would those slides will be in order to understand the role of virtual twin and how it can help industries for go to market faster. Also, we'll touch upon system. Basically, it has two aspects. One is emission and the other is susceptibility. So without influencing surrounding devices, if it caters to, then it's called emission. And if it caters to any equipment, if it caters to being influenced by any other equipment or the any other equipment in vicinity, it is called immunity susceptibility. In emissions, the effect of equipment signature on the surrounding electronics is studied. The device should not interfere with other systems, and other systems should also not interfere with the device electromagnetic signature. So, so let us now talk about EMC, electromagnetic compatibility. So basically, if we are developing a system, it should be electromagnetic compliant. What does it mean? Neither it should influence others. This electromagnetic signature of that equipment should not interfere with other electronics signature, and neither it should be influenced by the other electronic equipment signature. So that if we are able to comply with, it is known as electromagnetic compatibility. So here emissions and immunity is a well-regulated area. So like we have different regulatory standards, some regulatory organizations are there like FCC and European standards, which tells what will be the limit lines or what can be the maximum limit of emissions which can be produced in the environment or how much it can sustain. So such are known as the before releasing the product into the market, we have to comply to such standards. Now going further, automotive OEMs are there. So automotive OEMs also impose strict standard regulations on components. So the vendors which are supplying components to automotive OEMs, they have to be in strict regulation according to these standards. Then defense sector is there, which is quite stringent on to complying military standards. So in order to provide any equipment, or if you are manufacturing any equipment for military military, then we have to comply to such standards. Then there are general appliances, so day-to-day appliances which we use like home appliances, they also should fall under safe limits of operation. So such compliant, we have to adhere to such compliant standards in order to release the product into the market. So let's talk about the frequency range. So EMI/EMC, if you talk in general terms, it spans from low frequency to high frequency. Low frequency kilohertz to high frequency gigahertz. In kilohertz, what kind of products we will be seeing? We will be seeing SMPS, switched power mode power switched power supplies, switched mode power supplies. Then lightning. Then in megahertz, we come across EMP, HIRF, HIF, radio. And then in gigahertz, in high frequency, we'll be touching upon digital electronics, radar. So, in high frequency systems, we'll be seeing there is a lot of high speed switching. So I will be covering the switching part in the upcoming slides how switching, if it's high speed, how it will be going to produce emissions. So now let us talk about the motivation, like why do we need simulations? So first, it's an exhaustive and iterative correction process. So earlier, before like we were having simulations, what used to happen? We used to get requirements, then there was a concept stage, then there is a product development stage, and then we used to manufacture it into the market. So since we were not having any simulation tools in the starting, so the product was developed, then it used to go for testing, where it used to fail. So then simulations came into picture. So where it is used at the concept stage, and we can use that use the power of simulation, and then like prototyping cost can be reduced, and time to market will be lesser. So and earlier like high efforts and cost to correct is there. So the simulation will be reducing the efforts to get the product to the market, and yeah, the time to the market can be delay time to market, like to avoid. So I like to, like there is one poll query, so I would like, in order to make the session interactive, I have kept some polls. So please, the poll will be visible to you. Kindly fill it. Like, we'll have around 10 to 15 seconds of time. Okay, so we have around 60% people from transport and mobility, and 16% from around aerospace, and 11% people from high tech, and yeah, again 11% from industrial equipment. So yeah, we have a wonderful audience who are like from different industrial background. So now let's talk about the trends and issues that the uh, that different industries are facing. So let us talk about A&D industry, aerospace and defense. So what are the trends that we are seeing? So first is electrification, then multiple antenna placement and composite material usage. So as we are progressing in future, we are running towards alternative fuel to power our machine. So after the fossil fuel era, we are entering a clean and green energy era. So one such is battery powered flying machines. So such machines are quite advanced and loaded with many features. In such a scenario, many sensors, antennas are being used. So we'll be covering later for the A&D department what all issues that we are facing and how we can solve them, or we can rectify them. So with heavy advancement in technology, we are looking to composite material. So why are we looking for composite material? Composite material will make the body lighter, and hence it will help in taking flight. And these so now these technological advancement doesn't just come so easily. They pose many challenges. So what challenges are we talking of here? The first one, as we can see, EMC standard compliance. So all these equipments which we are providing for the A&D industry, they should be compliant with EMC standards like RTC DO 160, MIL standard 464, 461. Such standards should be complied in order to release the products, in order to use these products in such in this industry. Then there are high electromagnetic interference, or the like they will since it's going towards electrification, so more and more EMI signatures are there. So complying to that or mitigating them forms EMC mitigation. Then on antenna optimization. So we are placing different. So first of all, antenna as a entity, single entity should be optimized in order to perform good. Then it should be placed in vicinity to each other, or like there are, as you can see in the photo, there are a lot of antennas that are being used. So these antennas interfere with each other. So antenna placement also becomes a major challenge in this industry. Then in order to mitigate, we do post-site interference mitigation. So this is not this we'll touch upon later in the upcoming slides. Then the complexity of materials is being increased, due to which the antenna performance and is being affected. Then there are cable harness which is inside the airships, so which are responsible. So these cable harnesses are responsible for um, coupling the external indirect lightning effects into the airship, so which is a major challenge in this industry, and this also we will be like touching upon in the upcoming slides. So let's talk about transportation and mobility. Again here, as we are moving towards electrification, EVs, more and more electronic components are coming into picture. The electronics is being miniaturized. So because the electronics is getting miniaturized, the components are coming closer to each other. Closer components means more coupling of uh, signatures, or electromagnetic interference will be more. Then, so now we are also using ADAS as so. So we are using ADAS and radar sensing. So that is a trend that is going on. Advanced driverless assistance system. Then we have interconnected devices. So in order to make things more smarter, we are connecting more and more devices like mobile systems, and so mobile is used for parking, and so these kind of things are there, and more sensors are being integrated. So high integration of electronic sensors and ECUs. So what challenges is this transportation and mobility industry facing? Its first is high electromagnetic interference. So since many such electronic components are there, so they are interfering with each other, which is a concern, and we need to comply to them. So there are like stringent regulatory norms compliance is required. Then ADAS radar design and placement. So their designing as well as placement is a challenge in this industry. And yes, cable harness. So there are bundles of cables which are running throughout the body. So they need to be placed in a proper manner, because cables are major source of emission also, and they are major source of carrying those emission to other parts or other electronic equipments. So now high tech industry. So high tech industry, what are the trends that are there? 5G to 6G devices and networks, high speed signaling, flexible electronics, and miniaturization. These are the trends that are going on. And what are the challenges that this industry is facing? So antenna optimization and coverage, so signal integrity and power integrity, thermal management of PCBs and enclosure, and so these are the like challenges that this industry face. Now, life science and healthcare. So what are the trends in this industry that we face? So we have multiple sensors. Multiple sensors, why? In order to better diagnose an image. Then like multiple interconnected environments are there which are being connected. And what the challenges it is facing, since human interaction is there in this industry, so SAR values, specific absorption values, are taken into consideration. They should be within regulatory standards. And high electromagnetic interference, like suppose if you're using an MRI machine, like high magnetic field signature will be there. Then real-time test limitation is there, like uh, we can't put sensors inside human body, so this becomes a limitation for us. So here we require simulation. And then temperature variation in presence of fields. So fields will increase the temperature of the implant or tissues. So that is a challenge that we are facing in this life science and healthcare industry. So now one more poll will be there for you, so please have a look at it. You can tell. No problem. So yeah, I can see like people are there who are related to this industry, and they are like having 73% of people are involved in radiated emission simulation, 45 are involved in conducted emission, ESD 64%. Oh, that's great. BCI 27%. I have included an example of CE and ESD in my upcoming slides. So, okay, let's. So, this is my first example, DC-DC converter. So here what I have done is, there is a source, then there is a LASN network, then here this part is there. This is a 3D PCB which is present here. In this, a switching loop is there. So this is a spice file, and we can like use spice file for simulation in 3D. Then we have a load connected. So this is a PCB which we have imported in the form of ODB++ file. Then we are so here there are two variations to this simulation. The first one without EMI filter, and second with EMI filter. So in the upcoming slides, I will show you how the signature with and without EMI filter will be. And this filter was even developed by CST in order to check the real-time values and the simulated values. So if we talk of any workflow, so the workflow was like we just imported a geometry in ODB++ file format. Then we ran 3D electromagnetic simulation. Then we ran circuit simulation. So if you are wondering that why we are into like circuit simulation, so here there is a flexibility in CST where you can, if you can see these red portions. So these are ports. So you can place the ports in 3D, and in 2D you will get connections. Like you can connect electronic components like inductor, capacitor, spice blocks. You can connect in 2D. So CST provides a tight coupling between 2D and 3D solvers. So suppose when you are importing the PCB file, you need to change some values for the inductor, capacitor, or resistor, so you can change in the EDA layout. So while importing, you can change that. And so the like bifurcating the 3D simulation and 2D simulation, there is one advantage for it. Whenever like once the 3D simulation is run, then you the that you have added, you need to run the simulation again and again. The circuit elements or the electronic element only the circuit simulation. So this reduces your time to half of the simulation. So now here we could have run the simulation in 2D, like a 2D simulation also, but if we are running in 2D simulation, like a spice simulation, if we are running it, we won't be able to see parasitic elements, the contribution of parasitic elements. So for that, 3D electromagnetic simulation comes into picture, and it's important. So in this 3D EM simulation, it will run and calculate all the S parameters. Then in circuit simulation, we can just add the auxiliary equipments or the circuit elements, and then we can run the circuit setup. So if I talk about the different parts which are there in this DC-DC converter, the first one you can see is the EMI filter. So this will be switching on and switching off. Then there is a DC-DC circuit which will be converting 12 volt to 5 volt. Then the load is connected on this part. So now using the software, we just like imported the PCB and run few simulations. So this was a functionality check of the DC-DC converter, wherein we have input 12 volts and it's down converting those 12 volts to 5 volts. Since it's achieving steady state after 300 microseconds, so we will be running the simulation after 300 microseconds. So these are the input and output currents of the DC-DC converter. You can see the inrush current is there, so that's why there is a spike. And after 300 microseconds, it's coming to steady state. So all these kind of analysis is possible using the tool. And so this was the setup. Like I was explaining you different sections of the setup. So there is a switching circuitry where we have used a MOSFET, and we have used a MOSFET over here in a spice format. Then we have auxiliary components, load, LISN network. So this LISN network, if like you all will be able to correlate, like this we are using in when we are going for a real-time EMC simulation, EMC test. Then we use LISN network. Then we also have so two types of simulation were there in this, where we have used the EMI filter in on condition and in off condition in order to study the signature and the difference between them. So this is the EMI filter. So this was the thing which I explained, like EMI filter on and off functionality is there. There is a load which is attached. There are like auxiliary components to this. So like inductor, decoupling capacitors, Schottky diode, like input and output capacitors are there. Then switching circuitry, we have used MOSFET, and then LISN network is there, and then EMI filter is there. So when this simulation was done, so now this is the post-processing part, where the DC-DC converter without EMI filter is read. As you can see, the emission value is around 100 dB microvolt. Now this is when this EMI filter is switched off. Now when you switch on the EMI filter, the emission goes down to around 60 dB microvolt. So there is a difference of around 40 dB microvolt. So this was the these are the simulated result. So now this was again a part of post processing. So the one motivation which I wanted to mention earlier. So why do we like want to see simulation? One motivation for that is we can see the electromagnetic fields that are spread across the whole PCB, which won't be possible if we are directly going into a EMC test lab and doing the test over there. So simulation helps us or like tells us where the EMI signature is there, and we can mitigate it. So these are the two scenarios where with filter and without filter the DC-DC converter is being checked. So this is the result that we got. We have just superimposed those two graphs. So 40 dB microvolt difference we are getting. So now that was the simulated result. Now this result which I am showing, it's the measured result. So as I told you, like this DC-DC converter was fabricated, and then like both the um, like results were measured. So these are the difference between. So there is approximately 90 to 95% matching in the measured as well as simulated results. So the second example which I have taken over here is ESD. So by the example which I have taken, DC-DC converter as well as ESD, these are the most common example as well as tests which are run throughout the EMI EMC industry. So ESD, why? Because it's personal bond. So like since human interaction is involved, so a lot of times the ESD events will be happening or occurring. So here we have just made um, one like we have simulated a setup of ESD according to IEC 61000-4-2, and we have done the simulation. So this is the way how the ESD is done, like vertical coupling plane, horizontal coupling plane, and direct discharge we are doing. Same way how we are doing in real life, we can make it in the simulated environment and run those tests. So here what we have done is again the same PCB for DC-DC converter which we had taken. We are launching ESD pulse on that. Now this ESD pulse which we are launching, we are launching it through a ESD gun. Like how we do it in a real-time EMC test lab. The same way we have taken a ESD gun, we have grounded that PCB, and then we are launching the PCB pulse on this net. Then one element is attached from this net to the other net. On this we are seeing how much voltage is coupled. So now again there are two aspects to this simulation. One is without a mitigation technique, and with a mitigation technique, that is nothing but we have used a TVS diode. So the voltage waveform for positive pulse 8 kilovolt. So this is as per standard. So as standard says, it should be a double exponential pulse. So that kind of waveform we are getting out of the ESD generator that we have taken, ESD gun that we have taken. So in real time, how we give positive pulses, positive 5 pulses, and then negative 5 pulses. The same way it's generating the negative pulse as well as positive pulse. So this was in real time, and in real time EMC test how we do air discharge and contact discharge. So I have shown over here air as well as contact discharge. So these are the negative pulse that we got. So this is the contact discharge which we did, and the value, the graph is there. So now these are the like voltage waveform across the lumped element. So we are like targeting around -7 volt, but through the lumped elements it is flowing -5 volt. We are getting across the lumped element. Then so over here only we have just connected one. We have connected a TVS diode over here in order to mitigate, or in order to reduce uh, the effect of ESD pulse. So this was the difference that we got. So as you can see, like on the same PCB, we were able to do CE, conducted emission. We were able to do ESD. Like that, we can do radiated emission. We can put an enclosure, do radiated emission in it, do susceptibility simulation on that. So this way, we can like import any PCB or any equipment and run EMI MC test. So now let's talk about cable harness. Again, why we have taken this is cables up. Okay, so yeah, I would like to again put a poll. So there is a poll question for you. So I can see like 83% of people are like into CISPR, IEC, and EN standards, and 42% are in MIL and FCC, and 8% are there in SE. Okay. So now let's move ahead with cable harness. So why cable harness has been selected? Because cables are present everywhere. You take a big equipment, you take a small equipment, or multiple equipments are there. Multiple equipments are connected with cables. So cables are present everywhere, even on PCBs. There are not cables, but there are LANs. And there are PCB LANs which work as cables. So cables are present everywhere. So if we touch upon the cable harness simulation, so first we go in the logical design. So first we do a layout, like how the cable will be routed. So this is basically routing. So there will be a 3D routing. Then that, like first it's done in 2D, then you can convert it into 3D. Now here, once it is done, then you can select which all cables. So CST has a huge library for predefined cables. So there are predefined cables also, and we can make a cable by ourselves also. One more functionality is there. We can even import cables in .xml file or .kbl file. We can import them. So if we talk of cross sections, like whatever cable bundles you will be making, those cross sections you can visualize over here. So cross section design you can see. Then 1D EM simulation we do. So in this 1D EM simulation, we see S parameters and the cable. So we study the S parameters in 1D EM simulation. So cables are properly matched or not, that kind of results we can get. Then signal integrity we can check, like signal we are sending from one part to the other part, if it's reaching properly or not, that we can see. So signal integrity issues can be checked out, eye diagram can be made. So any distortion in signal is there, like when cables are being connected. So that also we can see. Then comes the 3D EM simulation part. So basically making a cable is a bit difficult. So CST gives you a edge over it, like edge over the designing part. So the cable shields and cable shield, the like material and all the properties you can play with. Then there comes the 3D EM simulation part, where cable will be either it will work as a source, or it can work as a sink. So yeah, and she like two kinds of simulation will be there: radiation and irradiation. So in radiation, it will act like a source, and irradiation means it will act like a sink. So cable shield should be good enough in order to stop the signals from entering inside the cable. So cables generally act like antennas also. So we have to be very careful when we are using cables. So this forms an important part of EMI MC, where cable laying, routing of cables, the signals or the type of cables that we're choosing should be taken into consideration. Then radiated field. So these cable act like sources. So there will be like radiated fields around, and we can check the radiated field patterns. Then shielding optimization, as we already talked, like so shielding, like how you want double braided, single braided. So all those braids, pitch lengths, and all that you can optimize in while doing the 3D electromagnetic simulation. Then yeah, one interesting part comes to this is bio-EM, electromagnetic modeling. So where you will use a bio or a human phantom you can use, and cabling will be there nearby the phantom, and how much the cables are radiating and how much the phantom or the phantom is nothing but human replica. So how much the tissue is, the human tissue is being susceptible by radiation, that you can check. The SAR values you can check. So since human interaction is there, so this becomes a bit crucial for us to see how the cables are radiating in an electromagnetic environment. So you can find various cable harness applications like robotics, like robots have that cable laying. Then in networking, you have a lot of cables. Then I've shown one MRI machine where you can see a lot of cabling is there. Then home appliances are there. All the high-end electronic circuitry, their cables will be present in airships, in any kind of vehicles. A lot of cabling is involved. So cables become a major source of radiation, as well as they also become a or they also carry noises from other environments, from one environment to the other. So they check, and if we can do prior simulation for that, then it's always beneficial for us. Now, cable harness application. So what all applications that we can see in this cable harness design? So crosstalk. If we talk of crosstalk, near end crosstalk or far end crosstalk, text or next, we can just analyze in like in graphical form. We can analyze it in CST. Then signal and power integrity, we can check the shielding effectiveness of the cable, like how much good the cable is giving isolation to the signal that is going inside it. We can check that. And moreover, shielding also ensures that the signal should not come out of the or start radiating from the cable. Then scattering parameters. Scattering parameters will tell us about like where the bends are there. Even we can do TDR analysis for these cables. So if any bend is there or like how the signal is getting distorted, all those kind of simulations we can do. Then characteristic impedance matching is happening or not. So all these kind of simulations, transient simulation, conducted emission as well as susceptibility we can do. Then coming to 3D simulation. So now since these cables are a source of emission, so we can do radiated emission tests, even radiated susceptibility tests, because these carry noises from one equipment to the other. So those kind of testing also we can do. The near field, far field, we can do surface currents and EMI MC. All these kind of testings we can do. Like we can just make these cables. Like two equipments are there which are interconnected by cables. We can make those cables in the 3D space of CST. Then we can run signals through it, and we can check if how it's radiating or it's irradiating. Then bio-EM simulation, as we talked earlier. So human exposure simulation you can do. Then specific absorption rate simulations also you can do. Then radiation hazards simulation also is possible. And so then like component level of simulation is also possible, and a full system level of simulation is also possible. So these were the like application of the cable harness. So cable harness comes as a module in the tool, and since cables are used everywhere, so we should keep a check on the radiation or the emission levels from the cable. So basically the workflow looks like this. You will have a cross-section design. First you will lay out the cable. Then you can have a cross-sectional design. Then you can run 1D simulation, uh, like where you will be getting the S parameters. Then there will be 3D simulation design. Like suppose over here I have shown that there is a car chassis. On that seat is placed, and on seat some cabling is there. So how much like it's radiating from there, that we can see. Then there comes radiated field, like what will be the far field pattern, since it behaves like an antenna. So what will be the far field pattern of it? Then bio EM simulation we can do. We can use a human phantom and then study the radiation effects on the human phantom. So now, as I told earlier, like we'll be touching upon this A&D industry, where we will be seeing the interference analysis. So not only like interference is not only electromagnetic, it can be RF interference also, where like different antennas are placed onto each other, and they are placed on the same platform. So like suppose here I've used an example of aeroplane body. So it is a single platform on which a lot of antennas are placed, lot of antennas with different frequency ranges. Some antennas are even identical to each other. One is the receiving antenna and one is the transmitting antenna. So in such scenario, co-site interference happens, like in single base, like uh, in same vicinity on the same platform, all antennas are there. So co-site interference happens. So this is known as RF interference. So this also should be avoided. So such kind of analysis is also possible, like where we get a violation matrix where different antennas will be there, and which antenna is interfering with which antenna we can find out. What all bands that are interfering, that also we can find out, and we can mitigate them. How we can mitigate them? Either we can increase the distance between the two antennas, or we can use a RF filter for it. So these are like few techniques which we can just use and find out the, or we can mitigate the RF interference. Then comes zoning analysis. So the electrostatic fields, suppose a lightning strike happens, so which all places in a aircraft are there which will be more affected by the discharge or the lightning. So that kind of analysis is known as zoning analysis, and that we can do easily in CST. We can just import the CAD geometry of any aircraft, and we can do the zoning analysis. Then one more analysis that is mentioned here is lightning indirect effect analysis. As you can see over here, a cable harness is present inside the aeroplane. So not only one, there are many cable harnesses inside an aeroplane. So this can be a single cable, or this can be termed as a bundle of cable. So here a lot of cables will be there, and if lightning strike happens, then it will be, so this cable, cable harness will provide a path of path to the lightning inside the aircraft. So there will be like some field patterns which will be formed inside the aircraft. So we should keep a check on such kind of radiations also inside the aircraft. So one such simulation is done over here, where like different field monitors have been placed. So what all like in order to capture the magnetic signature of the cables, cable harnesses. So such kind of analysis like lighting indirect, zoning analysis, co-site interference, all such analysis can be done using CST. So let's talk about like TNM industry, like how the interference analysis happens here. So as we talked earlier, the trends about the in the EV industry, where like the vehicle drive system is there, which contains DC-DC converter, AC to DC converter. So these converters work on switching frequencies. These switching frequencies are a major source of electromagnetic interference. Like so these, wherever these converters are used, which are using these switching frequencies and all, they form a major source of EMI. Vehicle ignition system, high voltage system generates EMI. So when any ignition is happening, so there will be transient. So transient always results in EMI. Then one more example is written over here, vehicle wiper motor system. So when the motor is being unwinded, or it moves in the opposite direction, then like reverse transient voltage also occurs. So here I have listed down some internal EMI sources and some external EMI sources in a car. So as you can see, like there are a lot of like multiple electronic equipments which are interacting with each other. Either like vehicle to vehicle communication is happening, or vehicle to other communication is happening. So like fuel control systems, CAN bus, electronic braking system, power steering module, airbag inflator. So these are all the internal sources. External sources, since I said like IoT is involved, so it's all interconnected. So cell phones, high power transmitters, Bluetooth devices, MP3 players, remote entry. So all these play an important role in like generating the EMI like interference. So now one more poll will be there. So you please answer it. Last poll. Okay, I can see. Okay, so the question was like CST Studio Suite can run only few EMC simulation. And it's like it can run all kinds of EMC simulation. So I agree with 68% of people. 23% of people can like we can collect and we can see what kind of EMI simulations you are trying to run and what you are feeling that it can't, like CST can't support. And 14% people, if you have any doubt regarding like what all simulations CST can run, we can collect. So yeah, so I'll be now summarizing like tool benefits. So what all tool benefits you can get using CST? So CST provides a comprehensive design solution. So from component level to system level, all kinds of simulation you can do. So you can have a full grasp over the like technology or any product that you are developing. Then it provides with unique functionality, and the GUI is very user friendly. Then multiple solvers and co-simulation is a major strength, as we like discussed earlier. Uh, like the co-simulation is nothing but the 2D and 3D that is that we are running. So those are the co-simulations. So those are a major strength of the tool. So let's summarize it. Simulations can be done at different levels. The first one at component level, then bench test. Bench test is nothing but you are putting a EMC test setup and running the test. Then full system level where like it's integrated with full system functionality, and then you are running the simulation. Then simulation provides ease of understanding physics. So here we are dealing with electromagnetics. So that was the physics behind which we deal with. So it's easy to understand when simulation is there. Then comes visualization. So you can see the electromagnetic fields, which you can't see when it's being tested, or in front of eyes. You can't visualize it. But software gives you a upper hand on that. You can visualize and you can optimize. As I told you earlier, like when we are importing anything, then we can optimize it. So optimization is always possible in simulation. So this was the summary. And like if you have any questions, you can please put it in chat.
We have few questions. The questions goes like this. What is EMP from Ayappa?
Okay, so EMP is nothing but a high altitude electromagnetic pulse. So these are generated like they're like classified into E1, E2, E3. Like three intensities are there. So they are like generated when like nuclear detonation happens. Then this EMP, HEMP pulse is generated. So yeah. So
The,
which is like nanoseconds, milliseconds, and which lasts in seconds. E1, E2, E3.
the next question goes like this. How accurate is CST simulations?
So CST simulations are, as I told you earlier, like I showed you one example in which we had made a DC-DC converter. So in those kind, like CST is basically 90 to 95% it comes accurate to the real-time results. So I can say CST simulations are quite accurate. Any other question?
Yeah, next question goes like this. How to do mitigation using the software?
Okay, so mitigation, if you are asking, then like, so what you need to do is you need to when you're talking of mitigation, you can run the bench test, or you can like uh, so actually the software is used to find out the areas where the test is failing. Then the software gives you visualization, so you can see what all components contribute in emission. So like that way you can see how to mitigate using the software. Any other questions?
The next question goes like this. Is this license-based or subscription-based simulation software? What is the cost?
Is this license-based or subscription-based simulation software? It's a license-based software.
Subscription also.
Subscription, yeah.
Okay. The next question goes like this. What all kind of simulations can CST run?
Yeah, CST can run like from low frequency to high frequency, like full spectrum simulation it can run. Like it can run multiphysics simulation also, like thermal, and particles dynamic simulation also it can run.
The next question goes like this. Explain about limit lines and peak detectors used in RE and RI and all.
So this you are asking with respect to CST. So yeah, like so in CST there is a post-processing template which like records, like after you have run the simulation, you can just run that post-processing template, where it will capture all the peaks which are like repeating, or like average detector is there, peak detector is there. So all such detectors are present in CST in post-processing template.
One more question we have. From what and all softwares we can import CAD geometry?
Okay, we can import CAD geometries from many softwares. Like if you talk of general extensions like IGES, DXF, all these from PTC Creo, Abacus, SolidWorks, and HFSS. So you can import almost all kinds of extensions and geometries from different CAD softwares.
Okay. We have last questions. What is the estimated time to plot electric field visualization EMPs at high frequencies?
Okay, so if you're talking of, so this is a, like this question can be answered in many ways. Like this question needs many inputs. Like what is the size of your simulation, or how much complex, or how much complex materials you have used in your simulation. So if the complexity is more of the of the uh, of the material used, then the simulation will increase. And if the size of the model is big, then also the time for the simulation will increase. So it's basically depends on many inputs for the simulation.
Are wave frequencies are also supported in this?
Yes, like CST supports from low frequency to high frequency. Full frequency spectrum it covers.
The last question. Only OBD files input is sufficient. What about IBIS models? Those tools provide standard library.
Yeah, you can import IBIS models also. ODB++ format is also like importable. Tool doesn't provide any standard library for IBIS, but you can import those and use it for simulation.
Well, we have more questions coming in, and we'll be addressing them one after the session. Thank you for your time, Anubhav, and your presentation. And thank you once again for all the attendees for your time and participation. If you have any further requirements, feel free to contact us. The webinar recording will be available on the YouTube channel soon. Don't forget to subscribe and follow us on LinkedIn for updates. Have a great evening. Please email us all the questions